Can you hear me? Okay. So good afternoon, everyone. Thank you for the introduction, and thank you, everyone, for being here. So I'm going to talk about the implementation of a deep learning algorithm for the reconstruction of magnetic resonance images, actually a particular type of magnetic resonance images, and developed everything on FPGA. How do I change? Thank you. So let me just start with a very brief introduction on what a neural network is, because I know you have already heard about it. But so in general, we can define a neural network as a function approximator. So a neural network can approximate any linear function between the input data and the target values. Now, a neural network is made of nodes that are represented as white circles in the diagram, and the nodes are organized in layers, and we have the input layer, of course, and the output layer, and in between we can have many different hidden layers. Now, the thing is that in fully connected neural networks, we have that every node is connected to all the other nodes in the following layer, and these connections are called links, and to each link we associate a weight that is represented with the letter W, and basically the weight represents how important that connection is. And to each node, we associate a bias that is represented with the letter B. Now, each node basically performs the same task that is represented by that equation there, is a weighted sum over all the inputs multiplied by the weights and summed by the bias. And then we have the activation function that we can have many different activation functions, but in our work, we use the ReLU function. Now, this is just the very basic principles of a neural network, but before using a neural network, we have to train it, which means that we have to find the best parameters, so the best weights and biases of the network. So first of all, we just give the network some inputs, and these data just flow inside the network until we reach the end, and we get our outputs, our predictions. And then we have to compare these predictions with the target values. And then to estimate how far these target values are from to estimate how the output of the network is close or far from the ground truth values, we compute the loss function. Of course, this loss function needs to be as small as possible, which means that the network at that point performs very well. And to minimize the loss function, we basically start from the end now and we go back. This is the so-called backpropagation. And at each step, we update the weights. And we compute the gradient of the loss function. So in this way, we are moving towards the minimum of that function, computed with respect to the weights and the biases. Now, if we look at the literature, we can find quite a few works of neural networks on FPGAs in many different topics. But all of these works, actually, the vast majority of these works are just about inference. So basically, they have trained the neural network in Python, MATLAB, or whatever, and they have taken the network and implemented it on the FPGA. But what about training on FPGA? Well, some of you may say, well, why would I need to train the neural network on the FPGA? Because the training process is in an iterative process. We can do it offline. We can do it just once. Once the network is set, it just works fine, and I just need to use it. And in that part, I need it to be fast and efficient. But what if training the neural network only once is not necessary? There are some cases in which we need to train the neural network more than once, actually very often. Let me just give you an example. Let's talk about my field, so magnetic resonance images. Since I don't know how many of you know about that, let me just give you a brief theory introduction on how they work. So let's just take a bunch of protons. Protons behave as little magnets, so if we put them inside of a strong magnetic field that we call B0, these protons will just actually orient with or against the magnetic field. Now, and this gives rise to a quantity that we call magnetization, that is our observable, what we measure. But if we stay in this equilibrium position, nothing happens. So what we do is perturbate the system by using another magnetic field perpendicular to the original one that we call B1. So what happens now is that all the protons will align with the B1 field, and the magnetization is now perpendicular to the B0 field. But this B1 field has a very short duration in time, so now it's gone. And what happens is that all the spins now will go back to their equilibrium position. And this process of going back to the equilibrium position is what we call relaxation. And we can look at this relaxation process along the direction of the B0 field, and we obtain the so-called T1 weighted image. Or we can look at the process in the direction perpendicular to the B0, and we obtain the T2 weighted image. Now, T1 is the time constant that dominates the longitudinal relaxation. T2 is the time constant that dominates the transverse relaxation. And this is exactly what happens inside our body. The problem with these images is that they are not quantitative. They are just qualitative image, which means that if I go and look at the value in each pixel, that number is just a number. It doesn't represent anything. It doesn't represent the real value of the T1 or the T2 of that tissue that I'm looking at. What if I need a quantitative technique? Well, we have it in magnetic resonance, of course, and it is called magnetic resonance fingerprinting. What is a quantitative map, first of all? Well, it is the opposite of the qualitative. So those images are actually called maps, because if I look at the intensity of each pixel, that number that I get is really the T1 or the T2 of that tissue expressed in milliseconds. And each one of us has different T1s and T2s, so with this technique, quantitative technique, we are moving into the direction of the personalized healthcare. And also, this technique is quite powerful because we can get more maps, more than one maps, with just one acquisition. How do I get these maps? Well, first of all, I need to scan the patient or a healthy volunteer, and then I can use a neural network approach. Our group developed this neural network that starts from the signal that we acquire with an MRI scanner, and it is a fully connected neural network, and it gives us as output those maps there. This network works really fine once it is trained, but the problem is that the training process of this neural network is really demanding. From a time point of view, it takes about 16, 18 hours to train this network. And also we have another problem. That is that this beautiful sequence here, magnetic resonance fingerprinting, is not standardized. And this means that if I change the hospital or the research center, now the process of reconstruction of the images is different because I'm changing all the equipment and everything. If I stay in the same research center but I change the type of scanner, then the process of reconstruction of the images is different. If I change the magnetic field strength, the reconstruction of the maps is different. If I change how I acquire the data, then the reconstruction of the maps will be different, and so on. Also, if I want to get more than 2 maps, I need to change everything. And each time I change something, I need to train the network again. So this is one of the cases in which training the network just once doesn't work really well. If I change something, I need to train the network again. So this is just one example, and it is what we are working on. But in general, we know the very good characteristics of FPGA, and these characteristics are actually making the FPGA very well suited for real-time applications, and especially in those cases in which we need extensive and repeated training, and in the case of a very large amount of data to be processed. So what are we trying to do? First of all, we have already done the first part, so the software part. We have developed this neural network that works really well, and it gives us as output the T1 and the T2 maps, the one you have seen before. And now we are working on the hardware part. So we are trying to develop this same neural network on the FPGA. What have we done so far? So first of all, we started from the original neural network, but we know that the resources of the FPGA are limited, so we had to reduce the network. So we just removed the first 2 layers, and we could do this because the training process is basically the same. You can see that the map is our loss function. The mean absolute percentage error is an error metric, and you can see that the difference between the original network and the reduced network actually is very small. So we could remove these 2 layers very easily, reducing the amount of operations that we need to do. Then we performed the quantization aware training just to see how the network would perform working only with integer numbers. And we can say that the quantized model, of course, uses lower precision, but this doesn't affect the network performance. So we can see the error metrics that didn't really change much from the original network to the quantized one. Now we are developing actually the real we are developing the network on the FPGA. So we chose a low-level approach, writing every firmware component in VHDL. And we started by implementing the operation performed by one single node in VHDL. That it was the equation I showed you in the first slide. And we just implemented that only once, because all the nodes just perform always the same operation. So you just need to call that module and use it again and again. And then we implemented the backpropagation process. These are just the development of the equations I showed you in the first slide. These two blocks, of course, are iteratively used to cover all the necessary operations to cover all the necessary operations to get our outputs from the neural network. Also, now we are not using any optimization technique, but we are planning to do so. And also, we are developing two different memories, one for the transmission of data, so PCI Express transmission, and one for the neural network internal variables. So some synthesis and resource estimation results. Those resources for the node are the resources required for 16 nodes of the network, and we needed to iterate over that block of nodes 31 times. And then for the backpropagation, these are the resources for just one part of the backpropagation, and we need to iterate over them 92 times. And from the synthesis result, we could see that a clock frequency of 200 megahertz is totally feasible, but actually we are aiming to 250 megahertz. Now, we also performed a simulation just to check whether our math that we implemented on the HDL was correct. And in fact, it is. You can see the results of the block of 16 nodes on the left, and the result in Python, sorry, and then the same nodes in VHDL, and the results are actually the same. And also, we performed a simulation for the PCI Express transmission, taking 1 minute and 28 seconds. Now, coming to the end, how long will the training take? Now, if we take into consideration the clock frequency of 250 megahertz and all the necessary times that we need to iterate over our blocks. So we have 56 clock cycles for one block of nodes. We have 250 millions of data to give it to as input to the network. And the same for the backpropagation, 104 clock cycles for one block of backpropagation, and we have 250 million backpropagations to be performed. And so if we do the calculations, we get a total training time of 200 seconds. So we are below the 5 minutes. So this is an acceleration factors of about 200 with respect to the standard CPU. So just to sum up, we have MRF that is a very powerful technique because it helps us to move in the direction of the personalized healthcare, providing these quantitative maps. And artificial intelligence plays a crucial role in these reconstructions of these maps, but the training of these neural networks is really demanding. So we are developing this hardware-accelerated neural network that is able to reconstruct these maps in a very short amount of time. And we are aiming for a clock frequency of 250 megahertz. And we are expecting to be able to train the network in less than 3 minutes. So this actually enables a real-time brain map reconstruction and gives actually the possibility, if successful, to have this hardware accelerator directly in the MRI scanner. So it is all from me. Thank you very much for your attention.
Thanks, Mattia. Questions?
Thank you for the great talk. And my question is, what is around the approximate bit width you are looking at here?
Sorry, I didn't get the question.
What's approximate bit width? The bit width of the parameters you are looking at for this training on FPGA? Accumulator bit width for updating the weights.
Oh, sorry, okay. So we have weights that are 8 bits, biases 32 bits, and all the other data 18 bits.
How about gradients?
How about, sorry?
Gradients.
Oh, they're just computed with the formula I showed you before.
No, I mean the bit width of gradient.
Yeah, it's 18 bits, also that.
Okay, so you are basically accumulating or updating the 8-bit weight.
Yeah, exactly.
And that will pose some very strong constraint on your step size, no?
Oh, yeah, I guess.
Because then if you do gradient descent, then
Yeah.
if the gradient is too small, you will just have like underflow.
Oh, yeah. I mean, we will develop some optimization techniques to avoid this, to try at least to avoid this issue. But yeah, we haven't tried it yet, so I don't know.
Okay. And another reason is what kind of application you are really looking on, because if you have MRI,
Yep.
there is a supervised training, and where's the ground truth?
I'm sorry?
Where's the ground truth like in operation?
Oh, we use simulated data. So we simulated, and so we have the actual value that we would get from the MRI scanner, and we know what the target value is. So we compute our ground truth values.
So the training is still like offline, in a sense?
At this stage, yes. We will use, once we have tested this and we have seen that it works, we will use real data.
And for the acceleration, you mentioned you accelerated like 7 hours to 5 minutes?
Yeah, from 16 hours to less than 5 minutes.
Okay, I have to recheck the math, but that sounds very amazing.
Thank you.
Maybe just a follow-up question on this. You're saying real data mean like we just have one person with their
Yep.
head in it?
Yeah,
3
volunteers,
minutes
yeah.
you train it? Oh.
Yeah.
Fantastic. Questions, okay.
Thanks for your presentation. I have some questions regarding the implementation. So you are implementing the network, and also you are implementing all the operations that you need to compute the back propagation and the gradients and everything, right?
Yep.
Okay. I'm wonder, what's the benefit of basically training the network on the FPGA if it's only done, for instance, once in a while? I understand the inference, for instance, but
yeah.
the training is like, okay, you can have GPU acceleration, but it's not that often. So
well,
how worthy is to spend all this time to implement that?
Yeah, it depends on what really you want to do with this type of network in a hospital. You can have very different scenarios, so you just don't really know. I mean, you could also just train many different networks and use the one that you need, but how do you know which one you need, and how do you know how many to train to cover all the possible cases? I mean, there are many different cases, and it's really difficult to cover all of them in a clinical scenarios, I'm thinking.
Okay, so basically the idea of having the trainer on the FPGA is because you need to train the network to each machine, let's say.
Yep, yeah, exactly.
Now it makes sense.
Yeah,
Thanks.
yeah. Every machine is different. Every sequence is different. So you also in the same hospital you can have different machines, and
Yes.
every machines work on its own, let's say. So it has its own working principle. So you would have to change everything, moving from machine to machine.
Okay, now it makes sense.
So you will keep the same architecture?
Oh, yeah. Yeah. Oh,
Okay, from
it depends
different
on how it performs, but
Okay.
yeah.
More questions?
For-
Okay, there's
for-
one in the back.
Can I ask the question? Concerning quantization aware training, what kind of data representation did you use? You specified that the bit width for the accumulators, but have you used floating points for quantization aware training, or was it full fixed point?
Originally, it was floating point, and then after quantization, it was fully fixed point. The integers, sorry.
So you implemented the floating point units on FPGAs for the computation?
No, the quantization model. The quantized model. So we performed quantization aware training, and then we took the quantized model and implemented that on the FPGA.
Okay.
Oh, great.
Thanks. I have just a very silly question. You mentioned that you have to retrain every time that you change the MRI machine, for instance.
Yeah.
Or some configuration of the machine.
Exactly.
Where do you take your data set for training?
We can simulate the data set. Basically, we have a code. I mean, one person in our group would develop this code that really simulates the data coming from the machine. Of course, simulating the data is much easier than acquiring the data because you would need many different people. I mean, you need 250 millions of data to train the network, so imagine scanning 250 millions of people.
Yeah.
Yeah.
Makes sense. Thanks.
More questions? Okay, if not, let's thank Mattia again.